So in that case, today we're going to have kind of like a chill, mostly chill discussion, especially because maybe I should have prepared better. So this is not a good example, maybe, of how these presentations should go. Some of the better examples maybe are some of the videos from past years, but that's okay. So we'll do a few slightly new things. Particularly, one thing I want to talk about is this point of what a minimal polynomial is, and some interesting fact about the minimal polynomial of upper triangular matrices. So actually, the reason why I want to talk about this is just there's a certain fact I want to prove about upper triangular matrices, but as of Axler's 4th edition, he kind of shows that there's a slightly bigger story to that than just this upper triangular matrix. So I'll kind of tell you the whole story here. But the thing I really care about for later is this fact about upper triangular matrices, which is quite clear. But okay, let's start with the minimal polynomial. And okay, first we'll start with just, we'll prove a theorem first. And the theorem is going to be as follows. So let T be some linear operator on some V where the vector space is finite dimensional. And the statement is that there exists Q, a monic polynomial, such that Q of T from V to V is 0. So it's some operator that's 0 in the vector space. So in what sense do I like, what do I mean by this? Well, if I have a polynomial, right, that's just some formal linear combination, right? Like Q of X is some kind of A0 plus A1X plus dot 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 plus ANX to the n. Do you agree? If I have a linear operator T, then I can take it and plug it in instead of X. Do you agree? And then what I would get is I would get another linear operator where by T to the n, I just mean apply T n times, right? A composition of a linear operator is still a linear operator, so Q of T will be some other linear operator, okay? So this is what I mean by this, okay? Does this make sense? Okay. So now I'll kind of run ahead a little bit and tell you what we're going to try and get at the end. So what do we know about polynomials of complex numbers? Yes. Yeah, so roughly, if I have a polynomial with complex coefficients, then I can always write it as like a factored product. Okay? And so this is hopefully, this will hopefully be related to this. So actually, I kind of started with the wrong thing. Well, I'll give you a plan for kind of what we're going to do, and then we'll just prove everything. Okay? And this is kind of the first theorem that we will prove. But the idea of what we want to do is, it turns out, this is something we'll prove later, but this is kind of the goal. It turns out that we're going to define this thing called the minimal polynomial and show that it exists. And this minimal polynomial thing, that's just going to be a polynomial like this, such that Q of T equals 0. So for a given operator T, there's going to be some polynomial Q of T that is 0. if I plug t into it. And it turns out that there's a minimal polynomial, so a polynomial of minimal degree that does this, okay? And it's unique. And it turns out, so we will kind of define the minimal polynomial, we'll show that one exists, we'll show that it's unique, so on and so forth. And it turns out, this is the second thing we'll prove, that being upper triangular is completely equivalent to the fact that the minimal polynomial can be factorized. Can be fully factorized as a product of linear terms. Okay? So roughly that q of t is equal to t minus lambda 1 dot 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 t minus lambda m. Okay? So we will show that being upper triangular is completely equivalent to this over any vector space, over any field. Okay? But then we will realize that, wait a second, for complex numbers, we know that any polynomial with complex coefficients can be factored like this. And we will then conclude that any upper triangular matrix, any matrix, well, any operator over V over complex numbers is upper triangular. So these are kind of the three things that we will want to show. This is our final goal, that if I have a linear operator over some finite dimensional Hilbert vector space, which is over the complex numbers, then any operator is upper triangular. That is kind of what point 3 is the goal. 1 and 2 is how we get there. And so in Axler's third edition, he kind of proves this point 3 directly. But then in point 4, he does it kind of by discussing the minimal polynomial first. And all these things are equivalent, but it's an interesting story to kind of realize that these two facts are true for any field, and then this kind of uses the fact over C at the end. Okay, that's the goal. Right. I should have maybe said something at the beginning. That do you have a question? Yeah.
Just a little confused. So Q is a polynomial from V to V.
Q is just a polynomial.
Okay.
You know, so it's something like this symbolically. Just some symbols. And Q of t, once I plug in t into it, it becomes a linear operator.
So t is like,
If I replace x, t is a linear operator.
yeah.
So you guys didn't discuss. Linear operator over V is a linear map from V to itself. Okay? So if I plug in, if I replace x with t everywhere, right, this becomes a linear operator.
Yeah.
Right? Because it's just a sum of linear operators to different powers. That's linear operator. Yes.
Okay. And then Q of t is 0?
Yes, Q of t 0 means it's the zero operator.
Oh,
It's an operator that takes any vector and sends it to 0.
Okay.
Does that make sense? Yes. Okay.
So Q of t is from LV to LV.
No, it's from V to V. Oh, sorry. Fixed t. T is fixed.
Oh.
And for a fixed t,
okay.
Q of t is an operator from V to V.
Okay.
That's what I mean. Think of Q of t as one whole thing. Yeah, so good question. I'm maybe not being too clear. Okay? So the minimal polynomial depends on the choice of t. You'll have different minimal polynomials for different t's, which makes sense. Okay? Okay. Okay. And I will actually maybe not prove this entirely. I'll maybe skip some steps, but I'll do the important thing. And then, well, the step that I find the hardest, and then the rest is kind of clear how you do it. I'll hand wave it. Okay, right. So I should have maybe made some comments about, this is supposed to be a reading group about quantum mechanics, right? And I'm telling you about something else. Maybe I should have started with this. I'll just make a brief comment now. Is a lot of what we do in like quantum mechanics, it has a kind of mathematical definition that people have realized what this mathematical formulation of quantum mechanics is over the years. And essentially, this mathematical definition of quantum mechanics says that quantum mechanics is something about studying certain linear operators over certain special vector spaces over the complex numbers. And those vector spaces have additional structure to it, which is closely related to kind of how you interpret quantum mechanics physically. But yeah, so vector spaces over complex numbers are essentially like that's what a lot like quantum mechanics is about in some sense. Okay, and we'll see. So the first couple of weeks is we're going to kind of develop the mathematical machinery to understand kind of all the basic things that you may need to know and prove all the basic theorems that you may need to know. And then we'll kind of dive into the physics. That's how I've structured it. Right. The other thing is you're probably most of you taking 247, maybe not, but a lot of all the content that we're going to cover, except for maybe today, is going to be in 247 for you. Actually, maybe not the linear functionals part. Linear functionals are next week, right? Like dual spaces.
Yes, sir.
Yes.
And I think there's a special topic for 247.
Oh, okay, yeah. Okay. I didn't know. I think, yeah. Okay, that's good. So regardless, everything you do here will be at least somehow relevant. Right. The other thing is I'm generally we're not going to do anything too fancy. Like we'll do basic things so that you understand basic things, and I think that's very good. But I guess some of the basic things we discuss are like maybe you wouldn't discuss in 256, you'd maybe discuss in 356 or something. Okay, anyways, so let's go back to our plan. First, we need to realize that there in fact exists a minimal polynomial and show that one exists. Before we get to minimal polynomial, let's show that just there exists a polynomial, right? Like there exists a polynomial. Monic polynomial just means that the kind of highest degree coefficient is 1. Okay, and actually, not even this. Sorry, I'll edit the theorem a little bit. That the degree of the polynomial is less than or equal to the dimension of the vector space. All right, that's important. I'll do yeah, 2 more. Okay, so let's prove this fact. Okay, proof. And one of the reasons why I want to, like, usually with this reading group, whenever possible, I will try and kind of, well, oftentimes I'll ask people to not prove things explicitly, but just maybe give, well, in linear algebra, I'll always ask you to prove things explicitly, but if you stick around for like further reading groups, I often ask people to not prove things, but kind of draw a picture and use a picture to explain why it would work. Oftentimes because like proving all the details rigorously just requires a lot of definitions and takes too much time and distracts from the physical point. But particularly these proofs, I think you never really used this kind of proof technique exactly in 240. Maybe you did. I wasn't paying attention to what you did in your course, which is why I think it's kind of the idea of how you do these things is important. And the idea is that we will do things by induction on the dimension of the vector space. So proof by induction on dimension of V. So how will we do this? Well, let's start with the first thing. I guess Axler starts with V being a zero-dimensional vector space, but maybe that's not the most convincing. So maybe let's start with induction on dimension of V. So suppose suppose dimension of V is 1. Okay, what's the okay? Suppose dimension of V is 1. Then what's the minimal polynomial? For no, not quite. So let T be some one-dimensional. Let T be an operator on V, right? What does T do, Dylan? If T acts from one-dimensional vector space back to one-dimensional vector space, what does it do?
Transforms a vector.
Yeah, how? What's the transformation?
For one-dimensional.
So yeah, from a one-dimensional vector space back to itself.
Changes the size.
Yeah, so that is just
Multiplying.
multiplies by a number. Okay, so all this does is multiplies by a number, right? So it's really just T has to be equal to lambda I, right? Just by that's what it is. So in that case, what's the minimal polynomial? Yes.
Minus lambda I. Lambda is not.
Yes. So this means that Q of x is equal to x minus lambda, right? Right? If I plug in x and if I plug t instead of x, I get t minus lambda I. So this is going to be 0. Okay. Base case, we're good. Okay. So let me move to the other side. So induction step. Suppose the statement holds for any vector space V with dimension of V less than n. Right, so I'm doing what it's called strong induction or whatever. Doesn't matter. Always use strong induction. You will never be wrong. Okay. So good. Now, what do we want to do now? What's the idea between this whole induction on the dimension of V? What, like qualitatively, what do we want to do? Yes.
So that holds for n plus 1.
Yeah. No, well, in this case, show that it holds for n. Sure, but why do induction on dimension of V? Why does, like, what do we want to try and do now, since we're doing, yes?
Somehow reduce our space by
Exactly.
multiplying by good polynomial.
Exactly. I want to reduce my space to be something smaller somehow, right? And I have the induction hypothesis hold on the smaller part of the space, right? And then I could look at the other part of the space. Do you agree? And then it holds there too, and then kind of combine that together somehow to get it hold for the whole space, right? And I don't think this is quite an idea that you've explored in Math 240 as much as you should, because this is a central idea of linear algebra. You have a vector space, right? You want to prove something for it. So what you do is you kind of split it up into smaller chunks, prove it for the smaller chunks, and then somehow combine it to prove the result for the whole thing, right? That's a very important idea that I think you should have discussed a bit more, but that's okay. That's more of a textbook thing. Like Axler uses this all the time, versus the other book doesn't necessarily use it as much. Okay, so yeah. Okay, so let's look at the following. Let's take a vector v in V, all right? And now you've actually kind of seen this idea before. I think, in one of your very first problem sets in a completely different problem. But okay, let's look at v, then t of v, then dot 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 t to the dim v. Well, let's do t to the n v. Okay, and so I'm supposing that the dimension of v is equal to n. Okay, so I can look at this list. Okay, can someone tell me something about this list of vectors? How many vectors are in this list? You know, so I want to ask them. How many vectors are in this list? N plus 1. Good. So I know that these vectors are linearly dependent. So what I know that they're linearly dependent. So what we should do is take m such that v up to tmv are linearly independent. Okay, so take the first two vectors in the list such that the thing is linearly independent. Okay, and oh, sorry. Yes, that's right. So then, yes, no, sorry. Such that okay, take m such that sorry, I'm going to change my mind. Such that m minus 1 is linearly independent, but then v dot 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 tmv is linearly dependent. Sorry, this is what I meant. Okay. What do I have? If these things are linearly dependent, this means that there exists some a0 plus dot 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 plus am tm v such that this is equal to 0. Do you agree? Do you agree? Okay. So let's call this polynomial. Let's call this polynomial s of x. So s of x will be a0 plus dot 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 amxm. Okay. And what's one thing we know about the polynomial? The polynomial q of t, s of t, is, what does it do? It, if I act s of t on any vector t k less than m applied to v, I will always get 0. So k less than m, I mean like t to the power of k, where k is less than m. I guess I can write it like this. Less than or equal to m. Do you agree? Why is that the case? Hmm? Well, not quite. Like, I know that s of t applied to v is 0. But why is s of t applied to t to the k of v is 0? Yes?
Well, so you have a0 plus blah blah blah
Yeah.
plus am to the power of
Yeah.
times t to the power of m. When you take t to the k,
Yeah.
you kind of multiply them together, and you just like all of the degrees go up by k.
Yes.
And then you can take it out from the other side.
Exactly. So the point is that t commutes with t, right? Like doing t first or t first doesn't matter because it's the same thing. So this thing, I should be able to do t to the k s of t applied to v, right? Because it's multiplication here is composition, but which t I do first doesn't matter. So I should be able to kind of multiply it out in this order instead, and s of t applied to v is 0. So then, okay, it's 0. So that's the idea there. Okay? Good. But what does this mean? So we found a linear operator S of t, we found a polynomial S of t, which sends the span of v dot 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 t v to the m minus 1 to 0. Do you agree? So, yes? Okay. But what is this? This is, I kind of had my vector space V, do you agree? And I carved out a chunk which is spanned by V dot 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 T m minus 1 V. What's the dimension of this chunk? M minus 1, or how many vectors are here? M. So this is an m-dimensional chunk, and m is necessarily less than the dimension of V because, because we chose linear combination of n plus 1 vectors. Okay, very good. But now, what can I do? I can just look at the rest of the vector space. Do you agree? The rest of the vector space is going to have what dimension? N minus m, that's right. So this has dimension n minus m. Okay. But now, what can I do? I can, oh wait, sorry. I need to be a little bit more careful here. Right. What is the rest of this? Sorry. Let me just double check. I need to be a little careful here. So this is right. To the operator, sorry, range Q of t is invariant by t. S of t restricted to range of Q of t. Yes. Sorry. I'm blanking a little bit. Right, sorry, like just the idea is that now we want to kind of look at the operator, like find a minimal polynomial for kind of this part of the vector space, and then just multiply them together, right? But it's not so simple. Why? Because it's not necessarily true that T restricts to this subspace. So maybe T sends some vectors from here to here. And then that would be, so then I can't apply this lemma, this induction step, right? I need to have that T is a well-defined operator on my subspace before I can apply this. So sorry, there's like an obvious trick. If someone knows the obvious trick, can you say it?
What is the question?
So the question is that, what I want to do now is kind of use the induction step kind of on the smaller space and then multiply the two polynomials. But I can't quite do that because T is not necessarily an operator on this subspace, right? It might send vectors from here to here, and then it's not an operator. So I need to find a different space to...
Quotient. Quotient is your entire space.
No, that doesn't quite work. Actually, right. So what you then do, you then look, instead of looking at... Right, sorry, there we go. I remember. So now, instead of looking at... you don't quite look at this space because of the problem that I just pointed out. So instead, we're going to look at the... okay, let's use image of Q... Oh, sorry, not Q, of S of t. Okay? The image of S of t. Do you agree? This is some subspace, and this subspace will actually have a dimension of at most n minus m, right? Because this subspace is part of the kernel of Q of t, right? Because just by how we set up Q of t, it sends this part to 0. So the dimension of this, not Q of t, S of t, sorry. The dimension of the image of S of t, this has to be less than or equal to n minus m. So that's good. And you know, yes, that's good. And the other thing that you know is you know that T has to send the T has to take the image of S of T and send it back to the image of S of T. Okay? How do we know this? So like the idea is T restricts onto the image of S of T. How do we know this? We've kind of done this just before, like the same idea. Like the idea is if I take a vector in the image of S of T and then apply T to it, then I'll get something that's still in the image of S of T. How do I know this? Yes. Yes, that's right. That's it. So let's the idea is that T commutes with S of T because it's all made of T anyway. So how do I know this? So suppose I apply T to something in the image, right? If something is in the image of S of T, that means there exists a vector V such that it maps to S of T of V degree. But then T and S of T commute, so I get S of T applied to TV, right? But this means this is some S of T applied to some vector, and so this has to be in the image of S of T. It's good. Do you agree? So now I know that T is restricts to the image of S of T, right? And so T is a well-defined operator on some smaller space. Okay. Now I can use the induction hypothesis, right? And therefore, so there exists a Q of T, right, such that Q of T restricted to the image of S of T is 0, okay, by induction. And also, I know that the degree of Q of T has to be less than n minus m. Do you agree? So maybe I'll define this as a Q with a twiddle. Okay, and so then I define Q of T to be S of T times Q twiddle of T. And the argument is this is the desired polynomial almost. Maybe I just need to divide it. I need to divide it out by whatever an is. But okay, I'll leave that detail up to you. Okay. The point is that we like it's the idea that's important. I had my big vector space, right? And I wanted to prove something for it. I knew it's true for a smaller subpart. I split the vector space into smaller parts, right? Proved it for each of the individual parts, and then kind of put it back together. Yes. The careful thing though here was once again that you can't like this whole of putting it back together is not always a simple step, because in this case our operator didn't necessarily restrict onto this kind of n minus m part. I needed to find like a smarter vector space to do this. Okay. Right, and the reason why this is 0 is because actually maybe I should write these in the opposite order. Do S of T and then Q of T, right? Because if I apply S of T to the vector, either it sends it to 0 or it doesn't. But if it doesn't send it to 0, then Q of T definitely sends it to 0. Okay. Yeah. Does this make sense? Okay. Questions? I think this will take maybe 15 more minutes and then we'll be done. I just had a very long preamble, I'm sorry. If you have a question, you can ask me. We're a room of 5 people. If you have a question, you can ask me. That's fine. These are compositions of operators. Yeah, sure.
The last thing there, are you multiplying the two polynomials? Or
So it's like I'm doing composition of this polynomial with this polynomial, but of t. But that will be the same as just multiplying the polynomials as like polynomials and then plugging t in. Like the point is like if I have say okay, suppose I have 1 minus t, I don't know 1 plus t, and I want to compose them. If you check at how you compose functions, right? It follows the same like what is it, FOIL method or what like whatever the rules for multiplication of polynomials. Functions, composition of functions follows the same rules, right? Why? Because okay, this function outputs 1. Of linear functions follows the same rules. Because this function does what? It outputs 1, and then it outputs this function outputs 1 of whatever vector, and this outputs t of whatever vector. Do you agree? And then I feed that into here. Do you agree? But that means that's the same as doing 1 of this vector, 1 of this vector, minus t of this vector, minus t of this vector. Do you agree? But that's just the same thing as multiplying polynomials, right? So it just happens that multiplying composition of, if I have a polynomial of an operator and a polynomial of another operator, composing them together is the same thing as multiplying out the polynomials and then plugging in the operator in the polynomial. It's the same thing. I agree. It's the first time you see it, it's kind of confusing. I didn't understand. I was confused about it at first in first year. So that's a perfectly valid question. Okay, but does that kind of make sense now? Yeah. Yeah, it works. The rules are the same, so you kind of say it interchangeably. Okay. Do you agree? Okay, so we achieved this statement. That's good. And we saw this new kind of interesting idea of how to prove this. Okay. I will now erase this part. So we've proved that there exists a polynomial. And the other thing that we showed, it's also of degree less than or equal to the dimension. Why? Because the degree of S was of m, and then the degree of q of t was less than n minus m. So that's good. We've achieved that. Now what we want to show is there exists. So the next statement, theorem slash definition. For any t of where did you encounter, before I go into this, where did you encounter a polynomial like this in 240? You did talk about a polynomial like this. I'll give you one more moment. If no one answers, you can answer. No. Well, what derivative? You don't have a notion of derivative. Yes, go ahead. Characteristic polynomial. Right. So if you look at the determinant of t minus lambda, that is in fact some polynomial that will send that will send everything to 0. Yes.
We haven't been told. We haven't taught Hamilton. We don't know that.
Yeah, exactly. You don't know that yet. But if you could spend some time and prove it. But the point is, a priori, the existence of such a polynomial has nothing to do with determinants, right? Determinants, and this is the whole point that Axler makes, and like he has written essays about this, he's presented at conferences about this. Like, determinants are not necessarily saying something about vector spaces in linear algebra. Determinants are something about volume. It happens that they, are a very useful tool, but a priori, like I showed you this whole story about how there exists this polynomial that sends the operator to 0, right? At no point did determinants ever appear, right? There's something about linear algebra. Determinants aren't necessarily something about linear algebra. There's something additional, but related. But they're not strictly necessary in everything we do in linear algebra. You can do everything without determinants completely. And it's arguably this is way more interesting in my opinion, but that's okay. Yes, I'm ideologically charging you with linear algebra like points of view, I guess. Okay, so back to the minimal polynomial story. For any t, any polynomial t, for any operator t, there exists a unique, unique minimal polynomial. Well, sorry. A unique polynomial, yes, of lowest degree. Such that, so polynomial q of x of lowest degree such that q of t, sorry, a unique monic, I'm sorry, unique monic polynomial q of x of lowest degree such that q of t is equal to 0, and we call this the minimal polynomial. Okay. I will not explicitly prove this fact right now. I won't write it down. I'll just kind of wave my hands and explain roughly what the idea is. Degree. So, what would be the idea? I know that a polynomial like this exists, right? Of degree less than the dimension of v. I know that one exists by the previous theorem that we proved explicitly, right? So then I can kind of go, okay, it's at a certain degree. There's finitely many degrees that are less than it, right? And so you just go down and say, okay, does there exist a polynomial of lowest degree of so say this is of degree m, and you say, okay, does there exist one of degree m minus 1? Yes or no? And then you just, okay, so there will, and then you go to the lowest degree up until such that after it there are no polynomials like it. Okay, so you know that there is something that's of lowest degree. And then you just have to show that there is a unique monic one. Okay, so you know that there is something of lowest degree. You can make it monic by dividing out by the highest factor. And then you say, okay, suppose there were two distinct polynomials that were in the same, that were both monic, right, and both sent q of t to 0. Then how you would do it is, okay, suppose you had two polynomials. That's okay, leave it. Suppose there were two polynomials of the same degree, both monic, that both sent q of t to 0, but had but were different somehow. Okay, q1 and q2. But this means q1 of t minus q2 of t was still 0 degree because each one of them is 0. But they're both monic, meaning that the coefficient of the highest degree for them is 1 degree, meaning that this together is some new polynomial q of t, which sends t to 0, of even lower degree, which is a contradiction to these being of lowest degree to begin with. Okay? So I'm not writing out all of the details, but this is the idea, right? For how one proves this. Okay? Okay. We're on time. And so now we've kind of prepared the machinery. So we now know that for any t over linear operator of a finite dimensional, a linear operator over a finite dimensional vector space, there exists this minimal polynomial thing. Very good. Okay. Good. And now we will prove the fact about upper triangular matrices. I won't prove the whole thing. One thing I will kind of defer to a tutorial problem from the past, but of course I think I only discussed it in office hour, but it's a straightforward thing to prove. Okay, can I erase all of this now? Okay. Yeah, let's erase that board. Yeah, we're good. And yeah, hopefully we can maybe sometimes schedule things at like 5 sometimes, so it's not too late. But that's one of the reasons why I get black tea, because it has some caffeine. And The speaker will always have a cup. The speaker doesn't need to worry about bringing their own cup for their own tea, but everybody else does. Okay, so now the last statement that I want to prove, well, the second statement. So the next theorem that we want to discuss is, let so T be in LV, then T is upper triangular, is equivalent to the minimal polynomial of T, can be factored as Q of T is equal to T minus lambda 1 dot 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 T minus lambda m, where lambda m is in our field. Lambda I is in our field for all of the i's. Okay, so let's briefly say about remind ourselves what an upper triangular matrix is again. Sorry, not an upper triangular matrix. That's clear. What an upper triangular linear operator is. So, definition: a linear operator is upper triangular if exists a basis v1 vn such that T of vj is in the span of v1 dot 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 vj. In other words, what this means is that if I write down the matrix of the operator in this basis, then the matrix will be upper triangular. So there will be kind of 0 below the diagonal, and then on the diagonal whatever, and above the diagonal also whatever. Why is this the case? Well, because remember, TVJ, right? What a matrix is, the column are the expansion coefficients of TVJ in terms of the rest of the basis, right? If TVJ is in the span of V1 up to Vj, this means that below the jth row, everything will be 0 because it's in the span of V1 to Vj. The j plus 1 doesn't contribute anything, right? So it has to be upper triangular. Right? So linear operator is upper triangular if there exists a basis with respect to which its matrix is upper triangular. Okay, straightforward. I shouldn't, I'm kind of saying these things. You probably know them. I'm saying them just for completion, so that I'm not skipping too many details. And maybe if someone watches the recording, they're fine. Okay. So, how are we going to proceed with proving this theorem? So, let's do, okay, the forward direction, this was a tutorial problem. T is upper triangular is straightforward. Can someone actually tell me what the lambda i's are going to be for upper triangular matrix T? If T is upper triangular, what are the lambda i's in the factorization going to be? Yes. Well, the eigenvalues. The diagonal elements. Yes. So why is this the case? It turns out if a matrix is upper triangular, then the numbers on the diagonal are precisely the eigenvalues. In fact, are all of the eigenvalues. And so that's something you can check. And so if you take the multiply T minus lambda I, all of the eigenvalues, then you will get a polynomial that sends T to 0, not necessarily the minimal. And then kind of the non-trivial step there is you need to show that if you have a polynomial that sends t to 0, q of t 0, then the minimal polynomial will divide that polynomial. So you can like factor out the minimal polynomial from there. That's a little bit non-trivial. I should prove it, but okay. That you get the idea. Like you can read it in Axler. I just want to show overall the ideas that we're trying to work with here, and then details maybe you can fill in a little bit. Okay. Good. So this direction is kind of easy up to the step of if I have some polynomial that tends to 0, then the minimal polynomial can be factored out of it. Okay. So let's prove the other direction. Proof of this direction. So suppose we have a minimal polynomial, and it can be written in this way. Okay? Let's show that then there has to be a basis with respect to which the matrix is upper triangular. Once again, we're going to proceed by induction on the dimension of V. By induction on dimension of V. Okay. So first, suppose the dimension of V is equal to 1. Do you agree? Then, once again, if dimension of V is equal to 1, that just means that that operator, all it does is just scale by some number, right? And if I know that it's t minus lambda is what kills it, then, well, okay, it's upper triangular. And I mean, it's always upper triangular because it's a one-dimensional thing. That's very easy. Do you agree? Every operator on a one-dimensional subspace is upper triangular. So done. Suppose it's true for dimension of V less than n. Okay. Take V such that dimension of V is equal to n, and let's work with this. Okay. So what do we know? We know that q of t is equal to t minus lambda 1 dot 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 t minus lambda m applied to v is 0 for any vector v. Do you agree? But what does this mean? This means that, okay, suppose I apply this to v, and okay, it's not 0, right? So it's either 0 or non-zero. Sorry. Suppose I apply this to v. It's either gets sent to 0 or it doesn't. Do you agree? If it gets sent to 0, that means that v has to be an eigenvector with eigenvalue lambda m. Do you agree? Yes. Okay. Okay, so if it's 0, then we have an eigenvector, we're done. Suppose this is not 0. Then, okay, it's some non-zero vector. Then I apply the next factor to it, and either get 0 or non-zero. Okay, if it's 0, I have an eigenvector. If not, it's not. Okay. I keep going like this, but eventually the thing has to be sent to 0. So eventually, like a bunch of these applied to v will be an eigenvector of t. Do you agree? So from this I conclude that there exists a vector, I don't know, vector u such that t of u is equal to lambda I u. So for some I, for one of these lambda i's. Do you agree? That's good. And so, yes. So, yes. So now, what I want to do is I want to pick a basis now, right? Such that t is upper triangular in this basis. Do you agree? And clearly u is going to be the first vector in my basis because it's, it's diagonal. So it's going to be, it's an eigenvector, right? So u is going to be the first vector in my basis. So once again, I want to use this idea, right, where I kind of have my vector space. I got this line u, like well, this is like a one-dimensional part, span of u, right? And then I kind of want to apply the induction hypothesis on what's left over, right? And have an upper triangular matrix there, and everything's nice. The problem is, we don't know that T necessarily restricts to the, to this other part. Maybe T takes something and sends it to something with U, right? From here to here. So we can't just quite do this. We have to be more clever about it. And the way that's more clever about it is very similar to what it was before. Okay, I'm going to go back to this board, if that's okay. I go back to this board, and I will say that what? T of, right. So I will now look at the following thing. I will look at, I will, it's a bit confusing, but I'll use now capital U to denote, or do I have to denote it? You know what, I won't denote it. I'll just say, okay, let's look at the image of T minus lambda I, where lambda I is this eigenvalue of this thing, okay? What do we know about it? So one thing we realize is that T minus lambda I, first of all, T restricts onto the image of T minus lambda I. Do you agree? That's one thing we know. Right, just by doing kind of the trick before, because T commutes with T minus lambda I. Sorry. U is sorry, give me a moment. This, yes. U is equal to T minus lambda I. This is the part that I didn't prepare. Right. Oh, good. Now, what is the next thing? Now, what we want to do is we want to apply the induction hypothesis, right? I want to show that there exists some minimal polynomial over here that will kind of send this subspace Q of T on this subspace to 0, and then get an upper triangular basis kind of on this space, and then I'll be done. Okay? Yes. Does that? Yeah. Okay. I'll make some other comments after. Okay. Good. So, how do I do this? Well, I have this polynomial for this problem, right? And what I can do is I can say, okay, let's take T minus lambda I and kind of take it out of here, okay? And look at what's left. So I can look at T minus lambda I, dot, dot, dot. I will omit T minus lambda I. If I put a hat on a term, that means it's not there. You remove it. T minus lambda M. Okay. And suppose I apply it to a vector U, where U is in the image of T minus lambda I. Okay? If U is in the image of T minus lambda I, then U is secretly equal to some T minus lambda I times V. Do you agree? Yes? But hey, here I had T minus lambda I removed. Here it appears again. So I get back the minimal polynomial from before. And so I know that this has to be 0. Do you agree? So I know that, okay, there exists a some polynomial Q twiddle sub I of T that is 0 on the image of t minus lambda I. Do you agree? And because I know that there exists some polynomial which can be factored, that can be factored in this nice form. So this is the part I'm not proving. I'm too lazy. But this implies that the minimal polynomial of t on the image of t minus lambda I also factored. Okay, so I'm not proving this fact, but because this polynomial is kind of factored, this means that the minimal polynomial also has to be factored. This is it's a theorem in Axler, like a couple pages before. Yeah, you can just look at it. Okay, but now what can I do? I can find a basis in which t is upper triangular on the image of t minus lambda I. Do you agree? So can I erase this part? Can I erase this part? Yes. Okay. And we're done now. This is the last few words. So by induction hypothesis, there exists a basis U1 up to UP of the image of t minus lambda I such that t is upper triangular, okay, with respect to this basis. And, sorry, is this the right conclusion? Yes. We have this. And then, okay, and then they just do it. That's right, okay. And now, right, I have a basis for this subspace, but I want the basis of all of V. Do you agree? So now, I just want to extend this basis. So, extend the basis. By, do they just do it by random vectors? Sorry, he doesn't have V's anywhere above. Okay, that's good. Yes. Okay. Extend basis by V1 up to Vm. So I have this combined basis now, this and this. And I need to now check that T is upper triangular in this basis. Okay? How do I check this? Well, I want to show that T of V, T of UI is in the UIs, and T of the VJs is also, so it is upper triangle. So it's clear that T of U, okay, so let's just compute it. So let's do T of UI, right? And I want to show that this is in the span of U1 ... UI, right? This is what I want to show. But this is clear. Why? Because we said that T restricts onto, so T sends vectors from here to here. Do you agree? That's what we said. So I know that, and in general, like by induction hypothesis, this basis is upper triangular, right? So this is true by induction hypothesis. This is U1 up to UI. This is UI. Sorry, this I is maybe different. I don't know, uj, whatever. Oh, what did you? Is that? Yeah. Okay. Good. And now, let's check that this is the same is true for t of vj. Okay. T of vj. The clever trick that they do is rewrite it as t of vj minus lambda I vj plus lambda I vj. Do you agree? This part is in the image of t minus lambda I. Do you agree? And this part, well, that's just in the span of vj. Do you agree? So this means that this can be written in terms of the uj's, in terms of the ui's, and this is just the vj. So this is in the span of u1 up to up comma vj, which is, of course, a subset of the span of u1 dot 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 up v1 dot 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 vj, as desired. Okay, so we found a basis, an upper triangular basis. Okay. And now we're done. Okay. Now, okay. Any questions? Yes? No? Okay. I know people want to leave, but good. So now we've achieved step 1, we've achieved step 2. Now I just tell you step 3. Step 3 is recall, and this is not something, you can read this in Axler if you want, or you can just assume, is this called like the fundamental theorem of algebra or something? Okay, sure. But recall fundamental theorem of algebra. Algebra. And the theorem is that, so any polynomial over C can be factored. Do you agree? But this means that any minimal polynomial, I mean, it's just a polynomial, I can factor it, right? That means I can write it down like that, right? So this means that so any T LV where V is over C is upper triangular. Okay. Good. So this is kind of the outtake for today. Sorry, I didn't maybe do a good job of motivating why we're doing all of this and how this will all later relate to quantum mechanics. This will be very useful. In particular, this theorem, I didn't prove it last year. I left this as like an exercise of read Axler and copy and like read the proof and like write it down yourself. Partially because last year there were people who didn't know Math 240, so we had to speed run like everything before in like a day or two. But the point is, like, in quantum mechanics, it turns out that it will be very important to find the eigenvalues and eigenvectors of certain linear operators. And one thing that will be of interest is we'll specifically study operators that have eigenvectors and eigenvalues, but have a basis of eigenvectors and eigenvalues. But we'll need to first prove that like a certain type of operators has them. And this will be an important step in the proof to show that, oh, these operators have an upper triangular basis by this theorem. And then we'll use a certain trick about those operators to see, if it has an upper triangular basis, then in fact that will also be the diagonal basis for those specific operators, right? So we'll kind of exploit a certain property of them and realize that their upper triangular basis, particular one, is also going to be their a diagonal basis. But we didn't get there yet. There's additional structure that we need to talk about and define. Okay. Okay, in that case, I'll stop this recording and